This is going to build a little bit on what we just did. This says ozone has a bond enthalpy of 143 kilojoules per mole. What wavelength of light can be used to break this bond? So here's the concept at work. We have ozone, which is a resonance structure, and it takes a certain amount of energy to break the bond. When we say 143 kilojoules per mole, that's if I'm going to break 6.02 times 10 to the 23rd bonds. That's how many kilojoules it'll take. The issue is when I want to find the wavelength of light using this equation, this is joules per single photon of light. So this is for 6.02 times 10 to the 23rd pieces, and this is for one piece. So in order to solve this problem, I need to take my 143 kilojoules per mole, and I need to convert it to joules for one single piece. So 143 kilojoules per mole is 143,000 joules per mole. I have part of my conversion done. Or 143,000 joules for 6.02 times 10 to the 23rd photons would be how much energy for one photon. So I'm going to divide by Avogadro's number here. 143,000 divided by 6.02 E23 gives me 2.38 times 10 to the negative 19th joules in order to break one bond with one photon. This is the number that can get plugged into this equation. So 2.38 times 10 to the negative 19th equals 6.63 times 10 to the negative 34th, which is Planck's constant, 3 times 10 to the 8th, which is the speed of light, over the wavelength. So 6.63 times 10 to the negative 34th times 3 times 10 to the 8th divided by my answer gives me a wavelength of 8.37 times 10 to the negative 7th meters. And the way light works is this is the minimum amount of energy. So anything with a wavelength shorter than this, less than or equal to this, will have sufficient energy in order to break that bond. This is the way the question usually shows up on the AP exam, some connection between bond energy and wavelength of light.